In this video, I'm going to try to introduce the concept of sampling. First of all, why do we sample? As many of you have already experienced, we see everything in the world. The real world is mostly experienced and affected by continuous time signals. And so the reason we convert this to a discrete data or discrete time simply is because it's easier in discrete time for us to save the data, work on it on a computer program, and then when we need to put it back out, we reconvert it to the continuous time. This process that goes from analog to digital in one direction is called from the continuous time to discrete is called analog to digital conversion, and the other way is of course called digital to analog conversion. Okay. And the reason we fundamentally do this is because when we have the data as numbers, we can save them much easier. And this is true of a lot of devices we have. For example, the music you listen to, the weather we collect, the laser intensity that we want to send out, the heat, everything is collected and stored in digital or the discrete time or digital data. And in order to do that, we have to take the real world data. It's going to be continuous, so we have to take every so often take a piece of it and remember what value it had and save those values. And this process is called sampling, of taking values at each point is called a sampling. So what we're going to spend in this chapter doing is trying to understand how that process actually works mathematically and how the signal is saved, how do we know when the signal is, and how mathematically we represent that data. So let's go ahead and look at a little cleaner picture of this, which basically the real world is continuous time. We would like to convert to digital switch, so we use a analog to digital converter, and what comes out of it's called sample. Is basically each of these points comes out as a number that we save, and those are, in a sense, if you want to think about that, that would be x of t converted to x of n in the lingo we've been using so far. So x of t was continuous time when you sampled it, and sample is always happens regularly. So you don't have a case where you sample 1 second and you come back and sample 2 seconds. If you're going to sample, your system has to be very regular, sample on a regular basis, and we even have, that's called the sampling rate, how frequently it is done, or sampling period for the distance between the two samples in time. But nonetheless, so this is the discrete time value, and then we can process this information. We can serve it in a computer, we can process it, we can do whatever we want to do until we change it to our output, but our output is going to be, the y of n is going to be in discrete time. So now we got to go back, and if you want to affect something in the real world, like push a machine forward, or heat up something, or talk to someone, or whatever the case might be, we have to convert it back using a digital to analog converter to convert it back to continuous time so we can communicate it. So what we're really interested in this case is how do you take a continuous time and convert it. So let's back up. What we're really interested in, how do you take an x of t and make x of n out of it? And on the other hand, we are very interested in how do you take whatever the result was in discrete and convert it back to y of t so we can use it. So that's the essence of what we like to talk about here. So in doing that, we have some issues we have to think about it. For example, one of the questions would be, how often do you want to sample? So let's say we decide that the period we want to sample is t seconds. Okay, so our rate of sampling or the frequency of sampling would be 1 over t, and and this is the period for sampling. So this would be the period, sampling period, and this would be sampling frequency. All right, so if that's the case, then every t we're going to sample, there is a sample here, then there's a sample here, there's going to be another sample t second later, and on and on and on. And then k is just an inner set of integers going from wherever we started at 0 going to infinite, or we could even start it from minus infinite, go to infinite. So as we are sampling, the problem we're going to run into is that, and to illustrate the issue, is that we will lose some of the integrity or some detail in the data, because, for example, if we were to sample x1, x2, and x3, which are 3 different signals, we will get exactly the same value back for all 3 of them, because when the sampling is happening, they're all intersecting at some time. So that's the same point. So we are losing the shape in the middle of sampling, because you're only going to have a number for this sample, you're going to have a number for this sample, you're going to have a number for this, number for this, number for this. So if somebody asks you what happened in the middle of sample, your answer, your only correct answer is, I do not know what happened in the middle. Okay, so that kind of leads us into conversations we will have regarding sampling theorem and all that in future videos. But for now, we just want to know what a sampling is. So that's great. So we want every so often to pick up this signal, pick up what the value of our analog signal is. Now, how do we do that? Well, the way we do that is we use something called a pulse train, and that is basically, so pulse train is basically a simple signal, P of t, usually represented by P of t, and that is a summation of n going from minus infinity to infinity. Okay, so basically what we're saying here of an impulse of t minus some n value times t. So if you remember, the definition of impulse is when the inside of this becomes a 0, then and this t should be capital, because that basically ends up being the period which we will sample. Okay, so what this signal is going to do is going to be, at every time there is an integer value of n, it will sample. So what this will look like if we were to do that, this would be a time scale. So if, let's say, this is 0, at 1t, it will have a magnitude of 1. At 0, will have a magnitude of 1, because those are the places at t equal to 0. When n is equal to 0, it will be 0. At t, when n is 1, that would be 0, and on and on. So this impulse will look like this, and this goes on to plus infinity. This will be 2t, 3t, and then of course we'll have the negative side as well. That would work as well, negative 1 and negative 2. This is a very useful signal, and its name is pulse train. Just because it looks like a kind of a bunch of train cabooses, cars attached to each other. I don't know, somebody saw that. But anyway, so that's an impulse, or it's called a pulse train, or more completely, it's called the impulse train. So that's, we have it. Now, if I want, let's say, if I have a signal there, and I want to sample it, let's say this is x of t, and I want to sample it, all I have to do is I have to multiply it by this pulse train. And by the way, as you can see here, the period here would be t, the sampling, whatever that t is, okay? So from here to here, and on and on. So what happens that at this point, it'll pick up the value of the x at this point, this one will pick up the value at this point, this point, this point, and on and on. So let's say this is n, and these values are, let's say, -2, -1, 0, 1, 2, and 3, and on in either direction. All right, so that's how we sample, and what you're gonna get, what we call typically call xp of t, the sample of t. This is really, we can also eventually write it at x of n, and I'll show you how you do that. This is going to be basically whatever the value of x is up here, then down here, a little further down, and a little further down, and then maybe flattening out and back up. So we're basically going to have these values. Okay. If you want to plot it in a t, xp of t, this would be basically, this 0 would be 0, this would be t, this would be 2t, this would be 3t, and this would be 4t, and this would be minus t and minus 2t. And I forgot to write that this impulse is going to be our summation. It's going to be, actually, I just, now that we know what it is, I don't have to write. This is going to be our impulse train. Okay, so now the other way to think about it, if the x-axis, instead of calling it t, I had called it n, then I could put simply 4, 3, 2, 1, 0, 0, minus 1, and minus 2. So that you see now my x of p of t really becomes x of n. Okay, so that's how we create. That's how we sample. All right. So let's put a bit of a mathematics behind it. I think we have it, but just to be on the safe side. So what we did, we basically took the x of t, our original signal we wanted to sample. We ran it through a multiplier. We basically multiplied by this p of t. And what came out of this multiplication was xp of t, which is the sampled value of x of t, which is simply the multiplication of x of t, p of t. Okay? All right. Oops. I don't mean to roll this too much. All right. So that's what we are doing. So mathematically, how do you write that? So mathematically, this is going to be written as xp of t. Actually, we have it right there. Xp of t is equal to x of t times p of t, and then that is really a summation. Remember, p of t was a summation of n going from minus infinity to infinity of x of t getting multiplied by delta t minus nt. Remember, this is the sampling period, right? Sampling period. So that basically what it does is, if you look at this thing, this is going to be only non-zero at specific points when t is equal to nt. So what's going to end up is this summation gets reduced to n going from minus infinity to infinity, and then x of nt, and that there is our discrete value. Okay. So that's basically how we do it. And this going from here to here, you can try to convince yourself you understand what this conversion is all about. Anyway, so we've done that. Now we are to a place where we have our sampling done and we have our signal. So now we have our xp of t, the sampled the function is equal to summation of n going from minus infinity to infinity of x of nt. Okay, so basically what we are saying is that our xp of t is going to be the values of the function at these specific points on the curve, and the rest of it is lost at this point. Okay, all right, so it probably is a good idea to take a minute and do an example of what a sign would look like. So let's say somebody gives us a signal, and let me use a different color so it's a little easier to see, maybe a black. So let's say somebody gives us a signal, x of t equal to sine of 2000 pi t, and they want us to sample it. They also say, okay, tell us if you sample it at period let's say t of sampling equal to 0.5 millisecond. Okay, so we want every half a millisecond to sample it. So let's see what the equations would look like. If I want to sample it at every 0.5, that means I have to, my P of t, remember the P of t has to be, P of t was these pulses, right? These pulses. And if you remember up there, the P of t is going to be summation of, oops, let's go a little higher, summation of n going, let's say, from whatever we start sampling to whatever we stop sampling of delta t minus nt, in this case would be n over 2, might as well put 10 to the minus 3 because it's in milliseconds, right? So this is basically our t, right? This piece is a t. All right, so now we have our P of t. Our x of t is basically right here, so we're going to feed that in. We're going to feed that in, multiply those two, and what comes out is xp of t, which basically, as we know, is going to be summation of n going from minus infinity to infinity, x of n times t, which is n divided by 2 times 10 to the minus 3. Okay. So what does that look like? Well, let's draw it. Let's draw it. So what does the sine of 2000 pi t look like? Well, the first thing I got to do, I got to figure out what the period of this is. So the period for this is going to be 2 pi over omega, right? 2 pi over omega, which is going to be basically 2 pi over 2000 pi, or is basically 10 to the minus 3 seconds. Great. So I kind of have an idea. So my x, let's draw the x of t. So my x of t is gonna be t, and let's say period is gonna be 1 second, half a second. So if this is 0 in time, I will have a sign that goes up, down, and up. Oh, that's not a pretty sign, but you get the idea. And then of course this goes this way. This is going to be half a second. This is going to be 1 second. I didn't pick a very good time, so let me go back and change this to be, let's say, 0.25 milliseconds. Okay, I need a little more sample than half a second. It wouldn't look really good. All right. So then that means this is going to be divided by 4. This is going to be divided by 4 because the sample now is 0.25 millisecond, which means another way of writing this would be a quarter, 10 to the minus 3 over that second. Okay, so that's my t. All right, so that's what I've got. That means that my sampling rate, so let's do p of t here, and my p of t is gonna have sampling. Let's say right lined up. So you're gonna have 1 at 0. You're gonna have 1. Oops, they're all 1, so it shouldn't make any taller. 1 is gonna be at 0.25 millis, and if this is, let's say, millisecond. And this is millisecond also. Then another sample is going to be at 0.5, another sample is going to be at 0.5, 0.75, and on and on. So when I'm finished, my xp of t, one period of my xp of t is going to be, basically it's going to be, so let me use a different color here. So it's going to be whatever the value of x was at that point, which is basically this value. And then this is going to be whatever the value of x was right there. So it's going to be right something like that. And I probably should erase this so it just doesn't look like there's a line there. And then this one is going to hit 0. And here is going to hit down. And this. So when I sample this as 4 times the frequency of my x of t, what I'll get is look like basically this. And this is xp of t, or you can even call it x of n if you want, if you start numbering them as 0, 1, 2, 3, 4, and call this an n. If you want to call it like t, if you want to keep it in a time domain, this would be 4, t of sampling, this would be 3t of sampling, this would be 2t of sampling, t of sampling, and 0. And then of course if you have negative, you're going to go the other direction. So that is the data now. We have accomplished what we set out to do, which was to take an analog signal and turn it into an analog or continuous time signal and turn it into a digital or discrete time sequence. And that was what our goal was here with the introduction of sampling, figuring out where first, why we do it, because it's easier to save, manipulate the data, and then how we do it by taking our function, multiplying it by a pulse train, and that's how we sample say signal. What we haven't really talked about is so how is it okay that we lose the data between the two sampling period? How frequently should we sample in order to be able to recover our signal? And those are the stuff left for future videos.